Probabilities and compound events. Let's first take a look at complementary events. Suppose we look at rolling a die and we count the number of spots on the die. The probability of rolling a 5 is the number of 5s divided by the total number of outcomes, and we know that this is 1 out of 6. And then the probability of not rolling a 5 is the number of non-5s, right, of which there are 5 of them, out of 6. So keep in mind when you roll a die, a 6-sided die, these are the possible outcomes, right? 1, 2, 3, 4, 5, and 6. So the probability of rolling a non-5, there are 5 numbers that are not 5. Okay, so it's 5 out of 6. What I want you to notice is that if you take these two probabilities, so take 1/6 and 5/6, if you add these together, you get the number 1. And the reason for this is because these events are complementary. They're the complete opposite of each other. And they make up together all the possible outcomes of whatever it is you're trying to do. In this case, rolling a die. So we have another rule for probability. It's called the not rule. So first of all, the complement of event A is the non-occurrence of event A. And we refer to it as not A. And the relationship between the probability of A and the probability of its complement, not A, is given by the formula probability of event A plus the probability of not event A is always equal to 1. And if you solve this for the probability of not A, you get 1 minus the probability of A. So for example, in this previous problem here, if I wanted the probability of not rolling a 5 when we roll a die, we could have done 1 minus the probability of rolling a 5. And this would have been 1 minus 1/6, which would give us 5/6. And the reason this is advantageous is because it's a little bit easier to think about the probability of rolling a 5 as opposed to the probability of not rolling a 5. So in our first example here, the United States Geological Survey gives the 1-day probability of an earthquake occurring in certain parts of California as 1 in 10,000. What is the probability of an earthquake not occurring in this region? So the probability of not having an earthquake is going to be 1 minus the probability of having an earthquake. And this is equal to 1 minus 1 over 10,000. Which is 9,999 over 10,000. Or if you like, this is a 0.9999 probability, or 99.99%. If the probability of an event A not occurring is 0.67, what is the probability that the event does occur? So we know the probability of not getting event A is 1 minus the probability of A. Well, likewise, the probability of A would be 1 minus the probability of not A. Okay? So in this case, that's just going to be 1 minus 0.67, and this ends up being 0.33. Now let's talk about compound events. And let me give you an example of compound events. Suppose I ask you if you're taking a card out of a regular deck of playing cards, what is the probability of either getting an ace or getting a spade, right? Either one is okay. Now, if you count up all the cards that are aces or spades, you will see that there are 16 such cards, okay? So if you had a picture of all the aces and spades and you counted all those up, you would have 16 total cards. Intuitively, you may think that adding the probabilities together will give you the correct answer. But look what happens when we try this. So if you think the probability of getting an ace or a spade is simply the probability of an ace, which is 4 out of 52, plus the probability of a spade, which is 13 out of 52, notice that this gives you 17 out of 52, which I'm telling you is the wrong answer because we know the right answer is 16 out of 52. So why is this answer wrong? What happened here? Well, it's actually pretty simple. See, when you count the aces, you count the ace of spades. And when you count the spades, you count all the spades, including the ace of spades. So what happened here is we counted the ace of spades twice, which is why we got an extra number here on top, right? 17 instead of 16. So the way we can accommodate for this is to simply subtract off one of those countings, okay? So in general, we call this the inclusive or probability rule. If A and B are two events, then the probability that one or the other or both occurs is the probability of A or B equals the probability of A plus the probability of B minus the probability of both A and B occurring. So for example here, the probability of getting an ace or a spade, the correct way to do this, would be the probability of getting an ace plus the probability of getting a spade minus the probability of getting both an ace and a spade. So we know the probability of getting an ace is 4 out of 52. The probability of getting a spade is 13 out of 52. But the probability of getting an ace and a spade at the same time is 1 out of 52, right? Because there is one card in the deck that is an ace and a spade. And if you add these up, you will get the correct number, 16 out of 52. Now, I really like the card examples, but you can apply this rule to more theoretical examples. So here, suppose a survey found that 89% of households use a cell phone at home. 79% of households have a landline, and 75% of households have both a cell phone and a landline. Find the probability that a household from the survey uses a cell phone or a landline. So first, let's find the probability that a household uses a cell phone or a landline. So probability of cell or land. All right, this is going to be the probability of a cell phone plus the probability of a landline minus the probability of both a cell and a landline. So what is the probability that they use a cell phone? Well, that was 89%, right? Because 89% of households use a cell phone. Plus, what's the probability that they use a landline? Well, 79% of households use a landline. Now, we know this can't be the answer, right? Because if you add these together, you get a number that's more than 100%. And probabilities can never be more than 100%. So that's where the subtraction comes in. We're going to subtract the probability that they use both a cell and a landline, and that's 75% of the households. So if we subtract these, or add these up and then subtract off what remains there, what you see is 93% of households have a cell phone or a landline, okay? And this is part A. Now for part B, we want the probability that they do not use a cell phone. So I'm just going to write probability of not cell. Well, we know this is 1 minus the probability of cell, right? This is just our complementary events rule. And this is going to be 1 minus, what is the probability that they use a cell phone? Remember, that was 89%, okay? So you could do 1 minus 0.89, which is 0.11, or you could do 100% minus 89%, which is 11%. Okay, so either way, it's 11%. Suppose A and B are events with the probability of A is 0.4, the probability of B is 0.35, and the probability of A or B is 0.65. So first we want to find the probability of not A or B. All right, so probability of not A or B is going to be 1 minus the probability of A or B. And this is 1 minus, what's the probability of A or B? 0.65. And this is equal to 0.35 or 35%. Now for part B, we want the probability of A and B. Okay, well, what's the probability of A and B? Well, let's remember the rule. The rule says that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So if I want to find this probability, let's recognize that this is what we're looking for here. I can solve for that in this formula by simply adding this probability over to the left side and subtracting this probability over to the right side. And if we do that, we come up with the probability of A and B is equal to the probability of A plus the probability of B minus the probability of A or B. And in this case, that's going to be probability of A was 0.4 plus the probability of B was 0.35 minus the probability of A or B, which they gave us was 0.65. So this is 0.75 minus 0.65, which is 0.10 or 10%. And that concludes this video lesson.